Hey guys, here's a video to go through some of the examples of what I was talking about today about the derivative itself being a function. So we were to start out with this function here, f of x equals 79.857 pi, right? So here's the graph of 79.857 pi. And my question to you would be is, what does the derivative of this function look like based on what you know about the derivative and it being slope? So I would ask, what's the slope of this line? And hopefully you would look at that and you would say 0. So if I'm going to graph the derivative at any point from this curve, what would you expect the value to be? Well, the value would be 0. So what I have set up here is if the point is a f of a, what is the derivative at that point? Well, it would be the derivative at this point would be 0, and the coordinates would be a comma f prime of a. In this case, it would be 0 for the derivative, and I just picked a random x value. If I were to move this point along the line, what do you suppose is going to happen to the value of the derivative? Well, hopefully you realize that no matter where you are on this line, the slope is still going to be 0. So if I animate this point, and you can see the derivative creating a horizontal line at 0. Okay, the y value is 0 if I'm trying to graph the derivative. So no matter what, it's also going to be a horizontal line, and it's going to be 0 no matter what I do with the original line. And that's only because this is a constant and it is a horizontal line with a slope of 0. So the derivative of this graph is this graph, y equals 0, or f prime of x would equal 0. All right, what if we ramp it up a little bit? Suppose we have the graph f of x equals 13.95x. And I would say, okay, what do you think about the slope of that line? Well, hopefully you realize it's clearly just a linear equation with a slope of 13.95. So if I were to pick a point here, a f of a, right, what would the derivative be? Well, the slope, as you can see, is 13.95, which is here. If I were to move this point somewhere else along the line, what do you suppose the slope would be? 13.95. So if I were to animate this point along this original function, what do you suppose would happen to the graph of the derivative? Well, if the derivative is going to be 13.95 at all the points, well then the derivative is just going to be a horizontal line passing through 13.95. The slope of this line is a constant 13.95, so the derivative is a constant value of 13.95. This is its own function. Okay. How about this one? We've done this one already, x squared, right? We know what happens. We did a 1, 1 a lot. Well, let's just pick a random point back here, a f of a. So the value is -5 or so. The derivative is about -10. So I'm down here. I have a negative value for f prime. I'm starting down here. What happens to this curve as a moves along? What kind of slope is this? Hopefully you look at that and you say, well, it's definitely a negative slope. But what's happening as you're getting closer and closer to this, this value, this 0? Well, the slope is getting closer and closer to 0. In fact, at 0, the slope you would expect to have for the tangent is 0. So this derivative value is going from negative, let's say 10, to like negative, 9 and negative 8, 7, 6, 5, until eventually it gets down to 0. So what's going to happen to the graph of the derivative? It's at -10, then -9, -8, 7, 5, whatever, until all the way 0. So this is going to look like a, just a linear equation there where the slope is changing, right? The slope is different for the original function here than it was all the way back here, right? Back here it was like -10. Here it's only like -4 on its way to 0. And then what do you suppose is going to happen the moment we get to 0? Right here. As soon as we pass 0, now the slopes are starting to be positive for the original curve. So my derivative is going to have a positive value above the x-axis, and it's going to go up at the same rate it was going up before. And there you go. So at any point, any blue point that I want, I could find the derivative at that point, and that would actually represent a point on the function that represents the derivative. So again, here the blue curve is the original. The pinkish or reddish is the derivative. And at every point on the blue, I have a derivative here. How about this one? What kind of slopes do you see here on the first part? Right, it's all positive. Eventually it gets to 0 again. Then what happens? It's all positive again. In fact, this particular original equation, I don't think there's any point, or I know there's no point where there's a negative slope. So what would you expect to see for your derivative? Your derivative is positive whatever here, 40 or so, right? As I move it closer and closer, it's going to get closer to 0. The derivative's going to get closer to 0, but then as soon as it gets to here, what's it going to do? It should bounce back up. So here the slope of the original function is positive, 25, 23, 22, 20, etc., right? It's positive. It's getting smaller positive, but it's still positive. That's why we're above the x-axis. Until eventually we have 0 slope right at 0. Right at 0, we're going to have 0 slope. It's going a little slow there, but you can see it. Right? Ooh, oh, can I get it? Oh, I missed it. I was trying to get 0, 0. So at 0, 0, we basically have 0 slope. And then all of a sudden, the slopes are going to be positive again, small at first, and then eventually really, really positive. In fact, it's going to start to look like a parabola. So again, the idea is you should be able to look at the original function and kind of understand how the slope is being affected, by that original function, and then think of what that derivative looks like as its own graph, as its own function. Okay? How about this one? What kind of slope would you expect on this part? Well, you can see it here. It is -1. What about at 0? Is that 0 slope? What about after 0? Positive, probably. So at this point, you probably can tell this is kind of like the first one or the second one, where the slope is -1 constantly, right? It's a linear equation. The slope is -1. But at 0, what are you expecting to happen? The moment we get past 0, the slope looks like it's going to be 1, right? Well, watch what happens. It jumps. This derivative is actually not continuous, right? Because it goes from, on the left-hand side, your derivative was -1, and on the right-hand side, your derivative is +1. It's kind of like when we talked about limits, but we're talking about derivatives, or differentiability, if you want. The derivative from the left is -1, from the right is +1, so there is no derivative at 0. We would say it's undefined, since the left and the right don't match. So this is one of those kind of special cases where you have a continuous function, but there is no derivative at every point. In this case, it would be at 0. Every single function that has a derivative must be continuous, but not every continuous function must have a derivative. That's the difference here. Okay, and then it just keeps going. All right, how about this one? All kinds of cool, crazy stuff. Try to just envision what's going to happen when I animate. Right here, you're expecting positive slope, of course. In fact, I actually have the value there. It's like positive 2,000 something up here. But what's going to happen from here to here? If you can visualize that, then you've already got the idea. If you can visualize what's going to happen to the derivative from here to here, you should know or be able to tell that this value on the derivative's function is heading down to 0. Okay, at this exact bump right here, I should have 0 slope, which means on the derivative graph, I should be on the x-axis. So watch what happens for the first part. Positive slope, but it's getting less and less positive until it starts to level out. Leveling, 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 right at the top there of the bump. I missed it, actually. I went a little too far. But basically, right at the top of the bump, right around -5 or so, you are going to have 0 slope. We're at -14 because it already, look at the scale, it's already just barely past it. Okay? And then what's going to happen? Now we have negative slope for a while, all the way to here. So this is going to represent a derivative under the x-axis all the way to here. So now we're going to be down here. It's going to be pretty steep at first. Then it's going to start heading back up, somewhere in between. So let's watch what happens. So negative slope, a little bit of negative slope, a little bit more. And then eventually it starts to level out of negative slope. It's still negative, but it's going to start heading back up to 0 because we know by -2 or so it's going to end up being 0. So right around maybe negative 1.5 or so, whatever that is, we should be back at 0. Let's watch and see how close we get. Almost there. It's doing a lot of calculations very quickly. Right about there. I almost got it. So about -1 3/4 or so, we're basically at 0. And then what happens? So from here to here, we have positive slope. Then it's still positive a little bit longer until eventually it levels out again. Then negative slope until it levels out to 0. And then positive the rest of the way. And you can kind of see that all happened. So the blue curve is the original, the red curve or the pink curve is the derivative, and the derivative represents the slope of every single point on the blue curve represented one by one so that it has its own actual shape and feel to it. Okay? So that's the main idea of this section. I will make another video that goes through a little bit of the notation, but this is the main idea of the derivative as its own function. All right, if you have any questions on that, be sure and let me know, and I will talk to you guys later.